My name is Kevin Vinsen. I'm part of the data intensive research group at ICRA. So I'm one of the guys who actually does crunch the numbers. As Kirsten says, the SKA is coming to Australia, and there are lots and lots of very difficult ICT challenges that we need to solve. The SkyNet POGS is a precursor project that we thought about 2 and a bit years ago about how we could distribute the work out as an alternative method to the traditional, here's a big storage array, here's a big computer, let's move the data from here to there, process it, move it back. But to really understand the problem, we've got to go back a step, and I'll give you a bit more detail about the SKA.
In a remote and inhospitable desert, something incredible is being planned. Something that will enable us to explore the universe, its past, and its ultimate fate. A masterpiece of scientific engineering that will be the world's largest, most powerful radio telescope. The Square Kilometre Array. The SKA will detect radio waves to reveal the hidden universe and answer fundamental questions about the cosmos. Its overwhelming size will enable it to peer deep into space, back to a time known as the Dark Ages, before the first stars shone. The SKA will reveal how the first galaxies formed from huge clouds of hydrogen gas, and will reveal the origins of supermassive black holes at their centers. It will survey the sky 10,000 times faster than existing telescopes to create a 3D map of galaxies in space and cosmic time.
Which means 10,000 times more data coming in.
This map will help us understand how galaxies evolve and how the acceleration in the expansion of the universe is driven by a mysterious dark energy.
Brian Schmidt won the Nobel Prize for that. And now, unfortunately, Ricky Ponting twisted his finger.
The SKA will search for gravitational waves, ripples in the fabric of space-time, by monitoring pulsars, the collapsed spinning cores of dead stars. These gravitational waves are generated when supermassive black holes interact. The SKA will also investigate how gravity behaves close to black holes.
Sorry, I'm deaf as a post, I can't hear it.
The unique sensitivity of the SKA will enable the study of radio emissions from the early universe that have passed through magnetic fields in space. This will help identify the origins of cosmic magnetism, a fundamental force difficult to study at other wavelengths.
Now this is a cool one. Everybody thinks, hydrogen.
And through its ability to detect organic molecules and investigate how other Earth-like planets are formed, it might even answer the question, are we alone in the universe? The SKA will revolutionize our understanding of the cosmos. It will take us on a voyage into the unknown. Who knows what else it may reveal?
So it's coming. 2 sites, 1 observatory. Now, for those of you who know about the NBN, you might be interested to see where we're looking at putting some of these remote nodes. They're actually NBN points as well. So we have to put the telescopes fairly close to damn good networking. Because as you'll see, we have got bucket loads of data. The South Africans are being a bit more ambitious. They're going across other countries. We can, in theory, go into New Zealand. Now, we get on well with the New Zealanders as long as we don't mention underarm bowling. Other than that, we get on fine with these guys. So we're actually even looking at putting one over there. As Kirsten says, we use mathematical tricks. This is called a long baseline. I mean, that's 5,000 kilometers. And that can really help with our resolution. Whoops, one too many. So, 1 observatory, 2 missions. Map the sky, and then look in detail for objects that we find. So mapping the sky will be done here in Australia. That's SKA Survey. And that one has got some huge data problems, as I'll explain in a little bit as a precursor. Now, I'm not sure whether to play this one all the way through.
Humans have all...
Because I think that Steve's got one that comes along that covers most of it off. So we'll talk just a little bit about the observatory. There it is, the Shire of Murchison. As you can tell from the accent, I'm originally from the UK. We invented the word Shire. And that Shire's bigger than England.
You're a little tall for a hobbit, though.
Do you want to see me toes? They're hairy. 41,000 square kilometres. Now, for those of you who are West Australians, something for us to remember. West Australia is 2.5 million square kilometres. Texans, who like to boast about their big state, it's only 696,000 square kilometres. We are considerably bigger than they are. I mean, that takes up a big chunk of Texas. It's our one little shire. But we have the Australian Bureau of Statistics, who do surveys. There are 114 people live in that shire, so our population density is 2 million people per square kilometre, which makes it a brilliant place for a radio telescope, because there's damn all out there. Nothing. I mean, you've seen the pictures that Kirsten showed. It is really, really empty. Just to put it into comparison for you, the rest of the world, Holland, the rest of the world, Australia in general, Alaska, Midwest, Greenland, Murchison. So there are more people in Greenland than there are in Murchison. Now, Kirsten talked a little bit about the SKA phases. SKA phase 1 is the thing that is the precursor to what the POGS needs to do. It's supposed to be about 10%. But that configuration will depend mostly on 1, budget, how much money is in the piggy bank. 2, technology advances, because geeks of the world are a brilliant species. They're always coming up with clever ideas, and things change. And we have to adapt to be able to cope with it. So we're looking, from the design reference manual numbers, about 250 dishes and about 250,000 arrays here in Australia. Now, what people don't realise is that damn great dish at Parkes is producing how many pixels? No astronomer can answer it. The open question, how many pixels do you think you get from that big dish? 1. 1 pixel. One of the great things about this step forward is we'll be able to scan the sky much faster. And science cases change, but it means that we can actually build bigger images. Now, for the dishes, we can go up to about 27,000 pixels per axis, and for the aperture arrays, about 28,000 pixels per axis per image. Now, depending on the science case, the number of channels will be different. As Kirsten showed with her little diagram, here's my version of it. That gap there is what comes through. Now, in optical light, we can do it with red, green, blue. Nah, we can't do that in radio because we've got just far too many of them. For the aperture arrays, I mean, the guys are that good. We could go up to about 1.5 million channels. So that's red 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, until 500,000. Blue 1, 2, 3, 4, 5 to 500,000. Green 1, 2, 3 to 500,000. I mean, that's an awful lot of channels. But we've got to keep all of them. So let's just take an average science case. So 27,000 by 27,000, maybe only 30,000 channels. We store floating point numbers because it's a voltage, essentially. That gives us 1 image, 80 terabytes. For the dishes, for the aperture arrays, it's even, we could go maybe 125 because we get better separation there. Now, remember in the video, it talks about magnetism. To record that, we need to record Stokes parameters and weightings, which effectively multiplies it by 5. So from one observation run of about 8 hours, we could, in theory, have 625 terabytes of data. 1. That's 1 day. Or 1 observation run, 8 hours. That's a hell of a lot of data that we need to be able to process. Let's just look at, these are the first year's numbers for the SKA based on the science cases. All right, the raw data numbers. Hope you all remember your SI units. Tera, peta, exa. So the bottom two are the interesting ones. They're the big boys. 425 exabytes for the pair of them. Now, the best will in the world, I mean, Amazon would love us to go to their storage and try storing that. The only person who wins would be Amazon shareholders. We can't store this amount of data, so we reduce it. Some of it we can actually do reasonably well. Other numbers are still pretty large. Now, let's just play a hypothetical game, because I like hypothetical games. Let's just take 3 of them, which come to about 500 exabytes. A Blu-ray disc is 50 gigs, 1.2 millimeters thick. How big is the stack of discs? Nearest 1,000 kilometers will do. Remember, seriously, look, 2 hearing aids. I'm deaf as a post.
Call it 15,000?
It's actually pretty close. It's 13,000. West Australians in the audience, how big is the West Australian coastline?
Very.
12,889 kilometres. So you know, we have here the opportunity for great job creation. If we put discs all the way around the coastline, everybody can have a job by the sea, just getting discs and feeding it back and forth. Now, let's start looking at some of the serious numbers that we've got to deal with. And one of the first challenges that we're going to be doing is trying to do this. These are the ingest speeds that we need to worry about. There's the bad boy, SKA survey. That's the ingest speed that's coming out of the correlator that we need to be able to achieve. That's a pretty big number.
That's not from the receivers.
No, that's from the correlator.
That's post.
Yeah, this is from the correlator. So pre that, it's even faster, and that's Steve's area. You know, you see how grey he is, he's only 22. The aperture arrays, you know, we've got a huge range of image sizes and numbers that we need to worry about. But that's the challenge that faces us with this. From the design reference manual, we're going to need something about 64 petaflops just to be able to do certain parts of this. And we're also looking at about 14 petabytes of data coming in for the UV buffers. These are just mind-bogglingly big numbers. On what operating system are we going to do it on? Windows? Nah! Linux!
Yeah, question. How do these numbers compare to the Large Hadron Collider numbers?
We're about 100 to 1,000 times bigger. But I'm an old man, you can tell by the grey hair. I was really excited back in 1997 when we got the first teraflop machine. Yes, 72 cabinets. I've got a Knight's Corner GPU accelerator now in the machine room that does exactly the same thing. Moore's law so far has managed to keep ahead of us. And you know, if we look at the trend, it's really doing quite well. You know, this is since 1993. That's the #1 computer on the planet. Number 10, number 50. You know, yeah, there's big technology innovations occasionally, but let's extrapolate. When ASCAP was first coming online, we needed something around the top 50, which we did. When ASCAP first came out, the computer that was needed for that, when we bought it, was in the top 50. It's no longer in the top 100. It's moved. But look, we're ahead of the game here. And it's a great race. I mean, for those of us who are a bit older, you know, we remember the arms races. Well, now we've got the CPU race, and it's between China and America. The Chinese are winning at the moment. That was the Americans, that was the Chinese, and they're continually jumping ahead of each other. Tianhin 2 is the current champion. Chinese word for Milky Way, I believe, which is a cool name. I like that. It takes the same amount of power as 17,000 homes to power this beastie. It's also quite cool. The colours change here depending on the power consumption. So if it's really working hard, it changes colour. But the Chinese have a secret weapon. Look at these Chinese engineers. They're German. These are guys from the University of Heidelberg who have been helping do an awful lot of this work. So, why the SkyNet? Well, we're going to have these huge data problems, and we need to find ways of offloading some of the compute that is important that otherwise wouldn't get done. And how could we do this? We wanted a systematic way of processing very large amounts of data. I'm going to have to update that now the PS4 is out. And this is just ASCAP, remember, so these numbers are much bigger for SKA Phase 1. And if you ever hear we are doing that, buy shares in Apple. Now that's a fairly awesome number. The best will in the world, you guys cannot type fast enough. We invented the SkyNet. And yes, we did pick the name deliberately for the connotations, in that my background is machine learning and astronomy. So if you suddenly find your machine starts talking back to you in a Norfolk accent, you know I've got to it. So,
Sorry, you just have to say, I'll be back.
What, in Norfolk? I'll be back. You see, the problem is most of you couldn't understand a Norfolk accent if I went back to my home way of speaking. So, POGS. Pan-STARRS is a survey telescope. It's a rapid response telescope that is surveying the whole sky and producing shed loads of data. And my colleagues at Baltimore, at Johns Hopkins University, were saying, yeah, it's great, but all we can do is look at one image. We can't do anything systematic about it. And I said, aha. Light bulb moment, we can. And we built the SkyNet POGS. So what we're doing is taking data from optical, infrared, and ultraviolet, and doing what's called a spectral energy distribution fit. I'll talk a little bit more about what one of those is in a minute. We want to look at about 100,000 galaxies, and we will fit each pixel of that galaxy, and we will put the data back into NASA's extragalactic database. So we're not just doing it for us, this is for the whole astronomy community. All this information will go back. To start with, we're looking at about 628 million pixels that we need to look at. That doesn't sound that much, apart from when you think that it takes 5 to 10 minutes to do one. So that would be between 1,000 and 2,000 years on my little laptop. And my little laptop's not really that good. And I'm not sure I'll be around in 2,000 years' time. And I think it'll be out of warranty as well. We've actually got real science going out. If you want to read a lot more detail about it, this paper, get it from archives. Because if you go to the astronomy and computing website, they'll charge you for it. Whereas if you get it from archive, it's free. So point you at that, because I'm a great believer in open information. So what are we trying to do? A SED fit tells us a story about what's happening in a galaxy. When we look at ultraviolet light, we tend to be seeing young stars. So that's good. If we see a lot of ultraviolet, we know there's a lot of star formation happening. Young stars are there. But dust absorbs ultraviolet. But it then re-radiates infrared. So we can also look at the jump in spectrums, some of the infrared numbers, and see how much dust we're seeing there around areas. Optical light can tell us various information about the structure of the galaxy. So we put this all together to give us a fit on it. And we're basically building an atlas of all the pan-stars galaxies. From that, we also then be able to do extra science, bulge disk ratios. Traditionally, it's only done using optical imaging. But we're able to see so much more. By moving into the ultraviolet and infrared and bringing it all together, we can actually get a better view of what bulge disk ratios should be, what the break radii should be. And we're also starting to now look at how we can integrate it into things like Galaxy Zoo. So we can actually get you involved. So you can do it. Because at the end of the day, the best classifier on the planet is still a human eye. The best one in the world, the best code I can write, I still cannot outdo somebody who knows what they're looking for and can look at an image. Now, Galaxy Zoo's been doing this for a few years, using Sloan images. Radio Galaxy Zoo is now out there, so you can get involved in all of these types of projects, and you classify these galaxies, because it tells us more of a story. We can actually calculate an awful lot of stuff, and this is just some of it. Star formation rates, amounts of dust, stellar mass, temperatures of cold dust granules, because what we're working from are real galaxy models. So these are models of how galaxies can form. And we're using a probabilistic approach to find out what we think are the most appropriate at each point. So, today, as of today, we have 7,000 users just using the POGS system. Now, SETI at home has 1.4 million. So we've got a way to go to catch them, but we are number 11 now. And we're moving up. We've got 17,500 computers. Einstein at home has 5.6 million. So again, we've got a little way to go. We've done 12,500 galaxies so far, which is about just over 98 million pixels. There will be a prize for whoever does the 100 millionth pixel, because it will be 2 people will get it somewhere in the world, and we'll send them some goodies for doing that 1 pixel. Because it's special, that one. We reckon that was a really special pixel. To sign up to it, there's the URL for you.
Or just go to TheSkyNet.org.
And I can see phones going and people tweeting. Tweet me, that's the thing to tweet, that one there. Tweet that. Get that one out to everybody. The more we get hooking in, the better. Or you could do it the old-fashioned way and go to the SkyNet. And again, there's the sign-up thing. But why Boink? And the image has vanished. Oh, great. Oh, image is on the next slide. All right, that computer costs $390 million and does 33 petaflops. That's a lot of money. Now, any of you happen to be rich mining magnates or bankers who are willing to donate that type of money? No? Well, we'll have to go for the cheap option then. All the Boink computers around the world, when put together, come to 8.3 petaflops, which puts it number 8 in the top 100 of supercomputers on the planet. So yes, your little computer can make a difference. And this is why we do this. My monthly bill for this part of SkyNet, well, actually, it's most of the SkyNet now because I took over the other bits. We host it all out through Amazon, is $400. Yeah, it's no comparison really, is it? You know, $400 a month compared to 390 million, nah. So we'll keep using this approach for the time being to prove our ideas out first. So how does this point flow work? It's actually really simple. I mean, there's no rocket science involved in this. You have a BOINC client that asks the server for some work. The server goes to the database, gets you some work, gives it back to the scheduling server, which says, okay, here's where you can get your data. Your client then goes to the data server, grabs the data, and processes. It's as simple as that. Which is why the bulk of my Amazon bill is network. Because I'm moving quite a lot of data here. And when the data comes back, it's equally simple. We say, here's some data, gets passed back to the back end, we store it. Thank you very much. It's as simple as that. Now let's start seeing the numbers. Well, there's the BOINC challenge that recently went through. One of the great things about the BOINC community is it's competitive, fiercely competitive. Astronomy Russia issued a challenge to everybody out there in the BOINC world. We reckon we can put, oh, hang on, let's do it with a Russian accent. Hey, comrades, we reckon we can do more processing than any of you. And the Americans said, yeah, right, come on. We're coming in. And SETI America came in and hit us with this. Now, you'll notice there's this huge drop just before it. And that was the Americans sucking every work unit they could out of us and not giving it back. Because from the start of the challenge, the credit is taken from that time. So they were queuing up thousands of work units to beat the Russians. The Australians were involved, the French were involved. It became a really big international thing. And as you can see, we went this enormous spike when the Americans started dumping their data back onto us. And then we leveled off. But the great thing about it is we've kept them. We've kept a huge number of these people, and they continue processing our stuff for us, which is fantastic. Active users, registered users, the difference between these two is these are people who've done something in the last week. One of the things with BOINC projects is I cannot lock you into doing my work. We can encourage you, and we do offer prizes, ranging from a trip to Murchison, as witnessed here, to T-shirts and cups. You'd be surprised what you can get for a T-shirt. One of our winners was in Turkmenistan. You should have seen the reaction I got from him. He was so ecstatic. We sent him a T-shirt. Now, not surprisingly, the dominant client operating system is Microsoft. Now, guys, come on, please, look who's number 2. You've only got to get another 200 machines out there and you can beat the Android users, all right? But you're coming third to the Android users.
So this is clients, not produced work units, right?
These are clients. So you're a Linux community,
You know
I
the
just.
reason for this? Crap support for the video cards that do the GPU stuff.
We don't use GPUs yet.
What? So that all Windows, that's all CPU?
This is all CPU. No GPU yet. I haven't finished writing it. But, come on guys. You know, I mean, how many people are at this conference? You could move into second place if you all sign up. This is BSD, which of course is OS X. And then there's these 4 oddballs down the bottom here. Well, that's Sun OS. Yeah, there is somebody with a Sun machine out there. There is one with OpenBDS. And there are 19, which I have absolutely no clue what they are. The signature I get back, I cannot make head nor tail of. Now, number of cores that they produce. 4 cores, surprise, surprise, isn't the big deal. But that one actually is real. That's a server farm in France. And he is number 5. He is the one who's coming up, because the way a BOINC process works, they run at 19 priority, so literally, if there's nothing happening, they don't interfere. They're quietly behind the scenes. So if there's nothing rendering, this guy is sucking down work units, which is why the French do so well. They've got that one, and there's also another, they've got a few 256 unit ones as well. But they're Windows server farms. Maybe it's a French thing, I don't know. Very surprised at that one. All right, so the basic architecture.
Back to Reed's point, not running on GPUs would seem to be a pretty critical.
Can't hear a word you're saying.
Not running on GPUs would seem to be a pretty critical.
Give us a mo, we'll come down to that.
That would seem to be like working only on the rest of it because, you know.
Wait a minute.
6,000.
Like the next slide.
Wait, you mustn't steal thunder. It's a very bad thing to do from presenters. They get very cross with you. The AWS architecture, we started off with a really simple client-server approach. I know James is in the room, but we didn't trust Amazon. You know, I mean, they're money grabbers. They take our money off us. We wanted to be able to move away. But, remarkably, it's brilliant. We really like it. We've actually now changed the architecture completely, and we use practically all of their infrastructure if we can. And the speed improvement has been astonishing, and the bill has gone whew, through the floor. The main difference is here. In the database size, you see, we only need 50 gigs now. I was running with a 4 terabyte database, and they were going ka-ching because you paid by the disk volume. So we've effectively got the whole kit and caboodle in here. So clients come in, we have on-demand AMI nodes, so if the load goes up, I spin off a few more nodes if I need it. If the load falls back, I turn them off again, because I don't need it. All done nice and automatically. We use S3 as a very simple object store. We just throw it into S3 until we need it. Then another one of these AMIs kicks off, aggregates the data, and puts it into the long-term archive as an HDF5 file. We've moved away from FITs. For the astronomers in the room, we do not like FITs. FITs cannot store probability distributions because you cannot tell how long they're going to be. And FITs likes you to know exactly how many X and how many Y. So this is all HDF5 storage. It also compresses a lot better. So, as Kirsten said, you can actually see what you did. So here's some of the images I did. Not particularly useful bits I processed, but these grey bits are all the bits I did. And as a user, you can go and see, and it's real, it's not like SETI at home, where you look at that pretty little graph that's going up, that you think, God, is that what I'm doing? Nah, it's not, it's just a pretty little thing. This is real. This is genuinely what you did. And that's how we know to give people prizes when they do the certain areas. But of course, being in the astronomy side, I actually tend to work only in black and white. You know, the colour is all false colour. It's also obfuscated false colour. Because until I'm finished with it, I don't want other astronomers coming along and taking that data. When it's in NED, that's fine. But until I've put it to NED, that's my data. And they can look at it, but they can't necessarily understand it. We both worked on M100, but I did more of it. And you've seen that one already. And there's some of the pretty trophies. But here's the Stellarium plugin. So you can actually plug in, see the galaxies that you've worked on, and there's your image associated with it. So you can actually go in and get complete feedback on what you did. So, coming soon, a GPU version, OpenCL based, will be being released when I finish writing it. The biggest headache is the code for this is in Fortran 77. And any of you who are big fans of Janinski and go-tos are evil, I will send you a piece of Fortran that proves him absolutely correct. It was written by Monsieur Lecotte and Madame Lepaste at the Institut d'Astronomie de Paris. And it's an integration program that's probably been around since the late 70s that just works, and nobody's changed it because nobody dares, because none of us have a clue how it actually works, which is part of the problem I've got in doing the translation, because I've got to move to C to do this type of thing. So getting those bits working correctly and statistically correctly is actually turning out to be a little bit more of a challenge. We're looking at alternative SED fitting methods, using Monte Carlo methods, so that we can have an ensemble approach. So we can say, well, for this data, we got this. For this one, we got this. And we can take a probabilistic viewpoint of what we're going. We're going to give special unobfuscated color maps for astronomers. So if you're registered as an astronomer, what you will see will be the unobfuscated version through the website. We'll be using IVOA gateway, so it'll be completely standards-based. If you've got Aladdin or any astronomy program, you should be able to query into it and get the data from NED based on this. And we're also going to be adding in another 16 more parameters to it for good measure. So, conclusions. Well, we've got huge challenges ahead of us. This is only a step along the way. We're now starting to look at the first set of data challenges for the SKA signal science data processing part. What we hope to achieve in the first challenge is to move more data across the backhaul network than Google can. And you'll guess who our partner isn't Google. So they're quite interested in actually doing this because that's something they'd like to blow a trumpet about. So then we're looking at this as a way of reducing risk. So we'll be streaming huge amounts of data. Well, I've got 98 million pixels here, and I can validate every one. So we can throw them in one end, have a huge amount of GPU compute at the other end, which is why I have to get this GPU thing fixed and working properly, so that we can stream as fast as we can, 98 million pixels in this end, process it all out the other end and reduce it as a simulation of what we're going to have to do for the SKA. Because we're going to be getting that type of volume of pixels coming in, and we're going to need to throw it out the other end, all processed nicely. So, I mean, you'll see a lot of the ICRA people, we almost have permanent smiles, because we get paid for doing this. We get paid for having some serious fun, and we've got 5 years of this to come. So for me, at 52, that's a nice slide into retirement, maybe. Nah, I'm not going to stop. I mean, this is too much damn fun. We're going to be doing this until probably the middle of the next decade, and continually jumping ahead, taking technology advances all the way through. So, any questions? Now, I am hard of hearing.
Curious that the antenna are all near NBN access points. NBN access points are going to be presumably quite radio noisy, well, specifically with people around them. Now, it's interferometry, so you do RF5 navigation, but is that it?
I mean, they'll be close. Close means within 50 kilometers. I mean, that's far enough away. But we have to remember, these things are so sensitive. That's actually not that far away. I mean, there's a beautiful picture that the guys at ANU did using MWA data. And they've got this lovely image of the moon moving across the sky. Hang on, I mean, the moon's a cold, dead rock. It doesn't emit radio. Well, actually, it's FM radio bouncing off the moon. You've only got to go past, Byford Armadale going south of Perth, and you've lost FM radio here. I mean, the MWA is that sensitive. It's a brilliant piece of kit. So, yeah, it's likely to be a problem, as are the diesel generators up at Murchison. There is talk of possibly taking a spur off the Dampier to Bunbury gas pipeline. I mean, we need 50 megawatts up there. That's a hell of a lot of power.
That's a lot of diesel.
And that's an awful lot of diesel, which is why the gas pipeline and the gas turbine is an idea that they're seriously considering. It's infrastructure things, but that's more handball that one over to Steve. Any other questions?
Have you been engaging with any storage vendors as to how you're going to be?
Yes, part of the next phase is the design phase, which is a consortia-based project. Now, the consortia that I'm working in is for the science data processing. Headed by the University of Cambridge, involves us, Cambridge, Heidelberg, South Africa, Intel, Cisco, DDN, IBM. Yeah, now, it's amazing when you've got a project like this, all the big names come out to play. They are very, very interested in what we're doing. Amazon, also one of our partners. I mean, damn, can't get time on the Palsy Center. Where can I go? Hey, guys, can I just borrow a data center? Because, I mean, that's the scale that we're talking about. And I kid you not, that first data challenge, we're hoping to take over before it's commissioned an Amazon data center to do that, just to see whether we can get that type of ingest rate close and what problems we're going to have, because they've no idea. They've never tried it in saturation like that, nor have we. So they're quite keen on it because it helps build their knowledge of their own sort of infrastructure, and we're quite keen on it because we can then go, oh, thank God we can do this.
Have you found anything very unexpected in your the data analysis?
We've found some very, very, very dusty galaxies, which is a bit surprising. I've got to go through and finish doing the trawl of everything. But we are, I mean, unfortunately, I've got all this huge amount of data, and then I have to back to a 6 nodes cluster, which I'm processing, doing the analysis on at the moment. Yeah, there's some very dusty ones, which are more dusty than we expected. The other things we're starting to find, as you saw from the M100, the star formation rates are a little bit more patchy than we thought, because traditionally what it was done, you would convolve the image down to a pixel. So the star formation rate for that galaxy is this. Well, now we've got these Pan-STARRS images. You know, I mean, that M100 image is 4,000 pixels by 4,000 pixels. So we can really get in quite deep now. The biggest problem we've got, though, is that the ultraviolet and infrared images, which come from GALEX and WISE, are about 3 pixels. Because the scaling, it doesn't match. So we're having some issues with that. The guys in Cape Town are helping us out with the WISE data. And you know, one of the thing, how many people here are astronomers? Yep, because I mean, you'll understand that the astronomy community actually helps each other. And if you say to someone, hey, can you do this? If they've got time, they'll try and help you out. And Tom Jarrett at Cape Town is trying to help us out now by getting the WISE images much better. I suppose, it's a bit like sort of the Linux community, Somebody says, hey, anybody know how to do this for it? You go onto the bulletin board and there's 100 answers. Same type of thing. Any more questions?
Thank you so much.